Okay, folks, buckle up. In 1962, we nuked the sky, and something happened that no one fully expected. Lights went out, satellites failed, and then we never did it again. So the question is, what did we actually hit? Get ready for a wild ride. We nuked the sky. 1962, the Cold War is at its peak. Tension is high. Technology is moving faster than anyone fully understands. And then, the United States does something unthinkable. They launch a nuclear weapon, not at the ground, not at a target, but straight up, 400 kilometers above Earth, into space. What happens next isn't what they expected. In Hawaii, streetlights fail, hundreds of them, all at once. Communications break down. Systems designed to survive nuclear conditions don't. Satellites begin to malfunction, and the sky itself starts to glow. Artificial auroras, colors stretching across the Pacific, lingering far longer than they should. Officially, it was just a test. Science, data, progress. But after this, it stopped. No more nuclear detonations in space, from anyone. And ever since then, one quiet question has remained. What exactly did we hit up there? Alright, so yeah, starting strong. We literally nuked space, which feels like something you'd only do after losing a very serious argument with another country. And to be clear, everything there is real. Starfish Prime happened. The lights going out in Hawaii happened. The sky glowing like it's loading a new level also happened. Now, the what did we hit part, that's the question we're exploring, not necessarily answering. Important distinction before anyone thinks we've discovered a secret ceiling above Earth. Now, let's get into what actually went down. What was Operation Fishbowl? So, let's ground this. Before we go anywhere near the theories, we need to understand what actually happened. Operation Fishbowl wasn't a random one-off experiment. It was part of a much larger program called Operation Dominic. 1962, height of the Cold War. The United States and Soviet Union are testing weapons at a pace that feels, honestly, a bit aggressive in hindsight. Fishbowl specifically focused on something new. High-altitude nuclear detonations. Not underground, not at sea, but in the upper atmosphere and beyond. The most famous of these tests is Starfish Prime. July the 9th, 1962. A 1.4 megaton nuclear warhead is launched on a Thor rocket from Johnston Atoll in the Pacific. It reaches an altitude of around 400 kilometers, and then it detonates. Now, the goal here wasn't destruction, it was observation. A scientist wanted to understand how nuclear explosions would behave in space, how radiation moves, how Earth's magnetic field interacts with charged particles. This wasn't just weapons testing. This was early space science, mixed with Cold War urgency. Because at that time, satellites were becoming important. Communication, surveillance, navigation. Whoever understood space better had the advantage. Now, here's something interesting. The name, Operation Fishbowl. At the time, it's just a code name. Military operations love strange names. Half of them sound like rejected band names, but later, people start looking at it differently. Fishbowl, a contained environment, something enclosed, something observed from the outside. Now again, officially, it's just a name, but it's one of those details that sticks in your head a little longer than it should. Because at this stage, everything made sense. We knew what we were testing. We knew why we were doing it. What we didn't know was what it would actually do. Okay, so far, nothing crazy. Cold War, big weapons, bigger egos. Let's see what happens if we do this energy. Now, Operation Fishbowl is completely real. Well documented, no mystery there. The name thing, I'm not saying it means anything. Governments name operations like they're picking words out of a hat, but it is a bit on the nose, isn't it? Also, detonating a nuke 400 kilometers up just to see what happens feels a bit like a scientific version of pressing random buttons. And as we're about to see, things didn't go exactly to plan. The Hawaii incident. At first, everything looked like a success. The rocket launched clean. The detonation occurred exactly where planned. Instruments were ready. Observers were watching. And then, Hawaii went dark. Not all of it, not a dramatic blackout like in the movies, just enough to make engineers very uncomfortable. Over 300 streetlights across Oahu failed almost instantly. Think about that. This wasn't a local power issue. This wasn't a storm. This was a detonation nearly 1,500 kilometers away, reaching out and interfering with infrastructure that wasn't even supposed to notice it. Alarm systems triggered. Communication systems glitched. telephone lines experienced disruptions, and the most important detail, some of these systems were specifically designed to withstand nuclear-related interference, and they still failed. Now, this is where it shifts from interesting to unexpected. Scientists had models, predictions, simulations. They knew there would be an electromagnetic pulse. That part wasn't surprising. But the strength of it, that was. It travelled further, hit harder, reached systems it shouldn't have been able to touch. It's like throwing a stone into a pond and watching the ripple reach the shore faster than physics said it should. And here's the subtle part. This wasn't chaos. It was controlled, measurable, documented, which makes it harder to dismiss. Because something in the upper atmosphere didn't just react, it amplified, and no one had predicted that. Now imagine being one of the scientists watching this unfold. You launch a test expecting one set of results, and instead, the planet responds differently than your equations said it would. And that's not just data, that's a problem. And if this was the reaction at ground level, then the real question becomes, what was happening where the explosion actually occurred? Because whatever happened up there, this was only the echo, and that echo was already louder than expected. And this was just the beginning. Okay, so this is where scientists collectively went, that is not ideal. Now the EMP effects were real, documented and stronger than expected. That's not conspiracy, that's just physics doing something slightly rude. And I think that's the key point here. Nobody expected Hawaii to basically go, excuse me, and flicker like a haunted house. Now, does that mean we hit something? Not necessarily, but it does mean our predictions were off. And when your predictions are off during a nuclear test, you pay attention very quickly. The sky that changed. If you thought this was strange up until now, this is where it becomes something else entirely. Because what happened next wasn't just measured in data, it was visible. Across the Pacific, the sky began to glow. Not faintly, not briefly, but vividly. Artificial auroras appeared, colours stretching across the night sky in places that should never see them. Hawaii, New Zealand, Samoa. Thousands of kilometres apart, all witnessing the same thing. Green, red, purple, waves of light moving through the upper atmosphere like something alive. And it didn't just flash and disappear, it lingered. For minutes, then longer. Then, in some cases, the effects persisted for days, even weeks in altered forms. Now, here's what makes this different. Auroras normally happen near the poles. Earth's magnetic field channels charged particles there naturally. But this was forced, created, injected into the system. And the system responded. The explosion released massive amounts of charged particles. And instead of disappearing harmlessly into space, they became trapped, held in place by Earth's magnetic field, forming something entirely new, an artificial radiation belt. Let that sink in. For the first time in history, a human action didn't just observe space, it changed it permanently, at least for a time. And the consequences didn't stop there. Satellites began failing. Some lost communication, others degraded over time. Telstar 1, one of the earliest communication satellites, suffered damage linked to increased radiation exposure. Now think about that. A test designed to study space ended up damaging the very technology we were putting into it. That's not just unexpected, that's feedback. The environment reacted to interference, and once again, we're left with the same quiet question. Not dramatic, not proven. Just there. What exactly did the explosion interact with to cause all of this? Because this wasn't just energy moving through empty space. This was something responding, and whatever it was, we didn't fully understand it. All right, this is where it gets visually cool and slightly unsettling. Artificial auroras, amazing. Also slightly concerning when you realise we basically forced the sky to do that. And the radiation belt thing is real. We accidentally created a temporary new layer of stuff around Earth, which is both impressive and maybe not something you want to be doing repeatedly. The satellite damage is the big one for me, because now it's not just light shows, it's consequences. Still explainable by science, but definitely not predicted perfectly. And when you start changing space by accident, you might start asking some bigger questions. The science explanation. All right, before we go any further, we need to ground this, because everything we've seen so far, as strange as it feels, does have a scientific explanation. At least, most of it does. When Starfish Prime detonated, it didn't behave like a typical ground-level explosion. There was no dense atmosphere to absorb the energy. Instead, it released a massive burst of high-energy particles directly into Earth's magnetosphere. Now, the magnetosphere is essentially a protective field. It surrounds the planet and deflects charged particles from space. Think of it like an invisible shield, but it's not solid, it's dynamic, fluid, sensitive. So, when those particles from the explosion entered it, they didn't just pass through. They got caught, trapped along magnetic field lines that stretch from pole to pole. And once they were trapped, they began to move, spiraling, bouncing, circulating around the planet. That's what created the artificial radiation belt. And those same particles, when they collided with atoms in the upper atmosphere, produced the artificial auroras. So far, so explainable. Even the EMP. That came from the rapid movement of the charged particles interacting with Earth's magnetic field, generating a powerful electromagnetic pulse. Now, here's the key detail. None of this was unknown. Scientists already understood the basics of these processes, but understanding something and predicting it accurately are not the same thing. Because the scale of the effects, that's where things went off script. The radiation persisted longer than expected. The EMP reached further. The satellite damage was more severe. Even Soviet high-altitude tests around the same time showed similar patterns. So, this wasn't a one-off anomaly. It was a repeatable but poorly predicted outcome. And that's where things get interesting. Because when science explains the mechanism but fails to predict the magnitude, you're left with a gap. Not a mystery, but a question. Why was this event so strange? Why did the system respond more intensely than expected? Because once you accept that something behaved outside predictions, you open the door to a different kind of thinking. Not reckless, just curious. And that's where the story begins to split. Alright, science hat on for a second. Everything here checks out. Magnetosphere, charged particles, radiation belts. This is all textbook physics, just scaled up in a way that made everyone a bit nervous. It's like knowing how a microwave works and then accidentally building one the size of a continent. The key thing is this: nothing impossible happened. But a lot of the things happened bigger, stronger, and longer than expected. And that gap between prediction and reality, that's where people start getting creative. Let's go there. The alternative interpretations. And this is where the story opens up. Because once you have a real event with real unexpected consequences, people start asking different kinds of questions. And sometimes they land in very different places. Now, one of the most widely discussed interpretations online comes from communities connected to flat Earth theory. And it's important to approach this carefully, not to endorse it, not to dismiss it outright, but to understand why it exists. Because the theory itself is built around a very simple idea: that Earth is not an open system, but an enclosed one. A structure, a boundary, often described as a dome or firmament. Now, within that framework, Operation Fishbowl looks very different. Instead of a scientific test, it becomes an attempt to reach or even break that boundary. The explosion at 400 kilometers, seen not as a detonation in open space, but as an impact, something hitting something. Now, to be clear, this idea sits outside mainstream science. There's no verified evidence supporting a physical dome around Earth. But it remains one of the most discussed interpretations of this event online. And once you look at it through that lens, certain details take on new meaning. The name, Fishbowl. To most people, just a code name. But to others, a description, a contained environment, observed from the outside, something enclosed. Then there's Operation Dominic, the larger program Fishbowl belonged to. Dominic can be translated as of the Lord. So, when some people combine the two, they see symbolism, not procedure. Again, interpretation, not evidence. Then there's the idea that the sky was changed, which, interestingly, is partially true. We did create artificial radiation belts. We did damage satellites. We did alter the near-Earth environment temporarily. Now, for most scientists, that's where the explanation ends. But for others, that's where it begins. Because if a single test can change the space around Earth, what does that say about the structure of that space? And finally, there's the idea of suppression. That whatever was discovered led to tighter control of the narrative around space. NASA was founded in 1958, just a few years before these tests. And after this period, the public understanding of space became more structured, more defined. Now again, there is no confirmed evidence that these tests revealed anything hidden or required a cover-up. But the theory exists and it persists. Because at its core, every one of these interpretations is trying to answer the same thing. That same quiet question we started with. What did the explosion actually interact with? And whether you approach it through physics or through speculation, there's still a gap. between what we expected and what actually happened. All right, deep breath. This is a part of the internet where things get spicy. Just to be super clear, the firmament idea is a belief held by some communities. It's not supported by mainstream science. But it's also not helpful just to laugh it off and move on, because these theories don't come out of nowhere. They come from people trying to explain something that feels unresolved. Also, I will say this, if you name something Fishbowl, you are asking for theories. That's just branding 101. But yeah, this is where curiosity splits into different directions. And now we need to pull it back to the evidence. The missing data. Now, here's where things get quieter, because after the light fades, after the systems recover, after the initial shock, we're left with the records. And what we have is incomplete. Operation Fishbowl was heavily documented, but like many Cold War programs, a large portion of that documentation was classified immediately. Data collected from Starfish Prime and the surrounding tests were reviewed, archived, and in many cases restricted. Some footage wasn't released for decades. Some reports remain partially redacted even today. And the people involved, many of them worked under strict non-disclosure agreements, which means their full accounts never made it into the public record. Now, to be clear, this is not unusual. This is standard procedure for military programs, especially during that era. Secrecy doesn't automatically mean something unusual was discovered, but it does mean this. We're not looking at the full picture. We're looking at a version of it, filtered, delayed, edited for release. And when you combine that with everything we've already seen, the unexpected EMP, the artificial radiation belts, the satellite damage, you start to notice something. There's a gap. Not on what happened, but in how completely we understand it. Because if everything was fully explained at the time, why does so much of the data still feel fragmented? Why do some records stop just short of conclusions? Why do certain details remain unclear? Now again, this doesn't prove anything, but it creates space. Space for interpretation, space for questions, and space for that same quiet thought to return. If everything was understood, why does it still feel like something is missing? Because sometimes it's not what's in the record that stands out, it's what isn't. And just when you think the story might settle into something explainable, something else happens. Something simple, something easy to overlook. But once you notice it, it changes everything. All right, so this is the part where people start leaning forward in their chairs just a little bit. And missing data always sounds dramatic, but honestly, it's kind of normal for Cold War stuff. Governments weren't exactly known for oversharing. But that said, it does create this weird situation where we know a lot, but not everything. And humans are terrible at leaving gaps alone. We see a missing piece and immediately go, well, something must be there. Sometimes there is, sometimes it's just paperwork sitting in a box somewhere. But either way, it keeps the question alive. We never did it again. Here's the part that doesn't need interpretation. After Operation Fishbowl, we stopped. Not immediately. There were a handful of additional high-altitude tests in that same period. But then, nothing. No more nuclear detonations in space. Not from the United States, not from the Soviet Union, and not from anyone else. Now think about that. This was the Cold War, an era defined by escalation. Bigger weapons, more tests, pushing limits constantly. And yet, this specific type of test ended. Instead, in 1963, just 1 year later, the Partial Test Ban Treaty was signed, banning nuclear tests in the atmosphere, in outer space, and underwater. Now, the official reasons make sense. Radiation risks, environmental damage, satellite disruption, all very real, all very valid. Because by this point, it was clear that these tests didn't just stay contained. They affected systems far beyond their intended target. And in the world of increasingly reliance on satellites, that becomes a serious problem. So from a policy standpoint, stopping makes sense. But here's where the question lingers. Because throughout history, danger hasn't always stopped progress. If anything, it's often accelerated it. So, when something is not just slowed down, but completely halted, it stands out. Was it simply caution? A decision based on risk versus reward? Or did we learn something during those tests that made repeating them unnecessary, or even unwise? Not what happened, not why it was strange, but what it means. Because if an experiment is never repeated, you have to ask yourself, was it because we understood it, or because we didn't? And if the answer is the second one, then whatever happened up there was enough. Enough to try once, and never again. Okay, this is the part where people go, wait, hold on. Because yeah, stopping nuclear tests in space makes sense. We kind of messed up our own satellites, which is not ideal. But at the same time, this was the Cold War. We weren't exactly known for being cautious, so the sudden shift to maybe let's not do that again is interesting. Now, is that proof of anything? No, but it is unusual enough to ask questions. And honestly, that's what this whole story is, not answers, just a very persistent why. What did we touch? Let's just bring this back quietly. No theories, no noise, just what we know. In 1962, a nuclear weapon was launched into the sky. It detonated hundreds of kilometers above Earth. It created effects that reached across oceans. It disrupted systems that were never meant to fail. It altered the space around our planet in ways we hadn't fully predicted. That's not speculation, that's history. Now, layer on top of that the artificial radiation belts, the damaged satellites, the unexpected intensity, the classified data, and the fact that after all of it, we stopped. So here's where we are. We know what was launched. We know where it detonated. We know what it did. But there's still something sitting underneath all of that. Something quieter, something unresolved. Because every explanation we have feels complete, but not final. Physics explains most of it. Magnetic fields, charged particles, radiation trapping. All of that checks out, but even within those explanations, there's an edge, a point where prediction ends and observation begins. And that's where the question lives, not in what we understand, but in what we didn't expect. Because something happened up there that went beyond the model. Not impossible, just unanticipated. And when something that powerful behaves in a way you didn't fully predict, you pay attention. So maybe this was just science catching up with reality. Maybe we reached into a part of the system we hadn't fully mapped yet. And once we understood the risks, we chose not to repeat it. That's the grounded answer, the comfortable one. But there's also another way to look at it. Not as a mistake, not as an accident, but as a moment, a brief interaction with something we didn't even realize we were interacting with. Not a barrier, not a structure, just a layer of reality we don't fully understand yet. And for a fraction of a second, we touched it, then stepped back and never tried again. So we're left with this. A real event, a real consequence, and a question that never quite goes away. What did we hit? Maybe nothing. Maybe everything behaved exactly as physics says it should. Or maybe, just for a moment, we reached further than we realized and found the edge of something we're still trying to understand. Either way, we've never gone back. All right, so this is where we resist the urge to go full movie ending and claim we broke reality. Because honestly, the science explanation does a pretty solid job here. But, and this is the fun part, it doesn't answer everything perfectly. And that little gap, that's where all these theories live, not in proof, just in possibility. Personally, I think we poked something we don't fully understand yet. Then collectively went, yes, maybe let's not do that again. Very scientific, very human. Also, probably a very good call. Thank you for watching, and I hope you enjoyed this one. And I've just started a second channel, Chronicles of the Drift, so please stop by and check it out, link in the description below. And if you'd like to support the channel further, I have Patreon and YouTube memberships, again, links in the description below. Also, don't forget to check out the Mysteria Archive podcast, available on the YouTube Music app. And as always, please don't forget to like, share and subscribe. It really helps out the channel and I'd really appreciate it. Okay, my friends, be safe, and until next time, stay curious.